Welcome to Learn Chemistry Together. This video is about Molecular Orbital Theory. Molecular Orbital (MO) theory uses mathematics as a tool to explore the consequences of atomic orbital overlap. The mathematical method is called the linear combination of atomic orbitals (LCAO). According to this theory, atomic orbitals are mathematically combined to produce new orbitals, called molecular orbitals. It is important to understand the distinction between atomic orbitals and molecular orbitals. Both types of orbitals are used to accommodate electrons, but an atomic orbital is a region of space associated with an individual atom, while a molecular orbital is associated with an entire molecule. That is, the molecule is considered to be a single entity held together by many electron clouds, some of which can actually span the entire length of the molecule. These molecular orbitals are filled with electrons in a particular order in much the same way that atomic orbitals are filled. Specifically, electrons first occupy the lowest energy orbitals, with a maximum of 2 electrons per orbital. In order to visualize what it means for an orbital to be associated with an entire molecule, we will explore 2 molecules, molecular hydrogen, H2, and bromomethane, CH3Br. First, consider the bond formed between the 2 hydrogen atoms in molecular hydrogen. This bond is the result of the overlap of 2 atomic orbitals, s orbitals, each of which is occupied by 1 electron. According to MO theory, when 2 atomic orbitals overlap, they are replaced by 2 molecular orbitals, each of which is associated with the entire molecule. In the energy diagram shown, the individual atomic orbitals are represented on the right, with each atomic orbital having 1 electron. These atomic orbitals are combined mathematically, using the LCAO method, to produce 2 molecular orbitals. The lower energy molecular orbital, or bonding MO, is the result of constructive interference of the original 2 atomic orbitals. The higher energy molecular orbital, or antibonding MO, is the result of destructive interference. Notice that the antibonding MO has 1 node, which explains why it is higher in energy. Both electrons occupy the bonding MO in order to achieve a lower energy state. This lowering in energy is the essence of the bond. For an HH bond, the lowering in energy is equivalent to 436 kilojoules per mole. This energy corresponds with the bond strength of an HH bond. Now, let's consider a molecule such as CH3Br, which contains more than just 1 bond. The molecule has many molecular orbitals, each of which can be occupied by 2 electrons. This figure illustrates one of the many molecular orbitals of CH3Br. This molecular orbital is capable of accommodating up to 2 electrons. Red and blue regions indicate the different phases. As we saw with molecular hydrogen, not all molecular orbitals will be occupied. The bonding electrons will occupy the lower energy molecular orbitals, while the higher energy molecular orbitals remain unoccupied. For every molecule, 2 of its molecular orbitals will be of particular interest. 1. The highest energy orbital from among the occupied orbitals is called the highest occupied molecular orbital, or HOMO, and 2. The lowest energy orbital from among the unoccupied orbitals is called the lowest unoccupied molecular orbital, or LUMO. Thank you for watching. Click subscribe to support this channel.